This is part 1 of chapter 3, Molecules of Life, and this is a basic introduction to macromolecules. When we're talking about the molecules of life, we're obviously dealing with biology molecules, and the biology molecules tend to be large molecules. In chapter 2, everything kind of deals with atoms and maybe water, so those are small molecules. Now what we need to do is build something bigger with those, and that's where the macromolecules come in. If you think of the very basics in terms of what is inside of a cell, then you realize that it's mostly water and then some organic molecules. So a cell is basically a sophisticated container. It's sophisticated because it allows things to go in and out. So a cell is not like a plastic bag. If you put something in a plastic bag, the expectation is that nothing oozes out and nothing enters, right? But that's not how a cell actually is. A cell is surrounded by a cell membrane. It's also known as the plasma membrane. And that structure is different because it is composed of molecules that interact with some of the other molecules in such a way that some can get in, some can get out, and there's control over what kind of things go in and out. Now, when you examine the molecules on the inside of cells, you'll find that they are primarily carbon-based. And so we can consider ourselves a carbon-based life form. And carbon is something that is studied very much in chemistry, and the study of carbon chemistry is the study of organic chemistry. And so in order for us to be able to really understand how living organisms work and some of the complexities associated with the processes that they go through on a daily basis, we need to learn a little bit about organic chemistry. This is not like a total college class in organic chemistry by any means. It's just bits and pieces of it that are relevant to our discussion. Now, the first thing to note is what makes carbon special. Carbon is an atom, as we've heard in the last chapter. There's a whole bunch of these, and they are arranged in the periodic table according to a certain scheme. Carbon happens to be the atom with the atomic number 6. So in that periodic table, it is the 6th one listed, which means it isn't very big. It has 6 protons, it has 6 neutrons, it has a mass number of 12, just for a little review. And when you look at the atom itself, it will have 2 electron shells, an inner shell which has 2 electrons on it. And why don't I just draw that for you so you can see. So here is the nucleus of the carbon, and in the nucleus are 6 protons and 6 neutrons. Okay, and then if you go around it, you have the first electron shell, and there is 1 electron and another electron, and then you have the second electron shell. And remember, what we're trying to do here is we're trying to balance the charge of the protons. There are 6 protons, therefore there are 6 positive charges. 2 of these electrons leave 4, so we must have 1, 2, 3, 4 more electrons. Now, on this second shell, you could actually have 8 electrons, but there are only 4. So it says here, it can hold 8 electrons, but it only has 4. So carbon would rather like to have 8, which means it is going to try and get 4 more from somewhere. And this is the thing that makes carbon versatile. It is not fussy at all about what kinds of other atoms it works with. It can work with hydrogen, it can work with oxygen, it can work with all of those kind of things that we talked about that make up the majority of the important elements of living organisms. So it can do all that. In very basic terms, we can say that carbon can form up to 4 covalent bonds. Remember, covalent bonds are electron sharing bonds. And therefore, it's going to be able to complete its shell. It has 4, it's going to attract 4, and therefore it's going to have 8, and that's what it likes. Now, let's get started with building some molecules that have carbon as sort of the linchpin of the whole deal. If carbon is allowed to share electrons with other atoms, what can we do with that? It turns out if we look at nothing other than having carbon and hydrogen, we can already create a huge number of interesting molecules. We can create things that are linear, we can create things that are branched, we can create things that are ring structures, and I just want to take a few minutes to explain to you how this electron sharing works. So when you look at this upper section here, you have the carbon skeleton, and of course here you see that there is a carbon, and the carbon here has 1 covalent bond, 2 covalent bonds, 3 covalent bonds, 4 covalent bonds, right? So this is what it likes. It has 4 electrons from other atoms that it's sharing with, and if you look carefully, it has its own 4 electrons. It has 3 that it shares with the hydrogen, and it has 1 that it shares with another carbon. Does everybody see that? 3 of the hydrogens from the hydrogens and 1 with another carbon. So that's, of course, one configuration. Now let's take a look at this one. This carbon here, it also has 4 covalent bonds, but in this case, it has 2 with hydrogen and 2 with carbon. So what we can say here, it has its own 4, and then it has 2 with the hydrogens and 2 with the carbons. Now clearly, this is different than that. The end result for the carbon is the same. It ends up with 4 covalent bonds, 4 electrons that it shares, and so like I said, it's not fussy. It doesn't matter where those electrons come from as long as we get them. So different configurations are possible. Then, building on this theme, you just add on to this. So the next one here has 4 carbons. 2 of these go according to that scheme. The ones at the end go according to this scheme. No big deal. But now we're using the same number of carbons, 4, 1, 2, 3, 4, and the same number of hydrogens, 4, 5, 9, 10. 3, 6, 7, 8, 9, 10, but we have a different structure. Do you see how interesting that is? Now you can play by sticking things out and making branches. And ultimately, there isn't really much of a change when it comes to the configuration. But look what happens to this carbon here. This one. It has 1 covalent bond with hydrogen. So it has its own 4. It has 1 with hydrogen and 3 with carbon. 1, 2, 3. So as you can see, this branching changes the configuration. Doesn't change the numbers of hydrogen, doesn't change the numbers of carbon, it's just the configuration. And the interesting thing is that whenever you change these configurations, some weird and wonderful things can happen. Organic chemistry is a fountain of these surprises. It's where there's all kinds of things that can change, that can be exchanged, that can look different, and so on. Especially when it comes to these weird things like here. There is now a double bond. What is a double bond? Well, a double bond means that 2 of these electrons around these carbons, they're doing double duty. That's a double bond. So instead of having only 1 electron shared with another carbon, carbon can actually share 2 electrons with another carbon. That's another weird thing. Like I said, it doesn't matter where they come from. It's not fussy. It's just what works. And so this is one way in which it can work. And of course, that changes the configuration. And here you have this double bond at the end. Whereas over here, you have the double bond in the middle. Any which way it works, right? Here then, you have a very interesting thing, a carbon skeleton that's actually formed in a ring. And then you just throw in a few double bonds. Here's 1, 2, 3 double bonds. And of course, you can see It's still a ring. The shape looks similar, but there must be differences in how these molecules interact. And that's what carbon chemistry is based on. You will see this as we go through the other portions of the lecture, where sometimes we have very subtle changes, very little changes, but the effect is very different. Makes for a completely different molecule, makes for things that are completely different what it can do. Now, all of this starts with the most simple of these kinds of molecules, and that one is the hydrocarbon. That one is methane. Methane is the simplest of these so-called hydrocarbons. A hydrocarbon is basically something that's only composed of carbon and hydrogen, hence the name hydrocarbon. Now, this is shown in 3 different versions, and the reason why it's shown in 3 different versions is because it's useful sometimes to look at the overall structure of one of these molecules. And here specifically is something I want to point out. If you look at the way this ball and stick model shows the position of these hydrogens and carbons, you see that the carbon in the middle is basically surrounded equivalently in sort of a pyramid shape by these hydrogens. So here is the space filling model, and you have a hydrogen here, and you have the carbon there, and you have another hydrogen, another hydrogen, another hydrogen. When we looked at water, we saw that we had an oxygen, and then we had a hydrogen, and we had a hydrogen. This here is different from that because on this, in the water, you actually have one end that has the hydrogens, and you have another end that has the oxygen. Here, whichever way you look at this, you're always going to have hydrogens and carbons. This one is symmetrical. It's a type of symmetry that makes this nonpolar. So this is not a polar molecule, whereas this one is. So again, fundamentally different in how they react. The last thing to do in this regard is to figure out how you can make these carbon chains a little bit more interesting. What can you do to a hydrocarbon to get it to react even in more different and wonderful ways? And the answer is simply by using some of those other atoms that are making up the top 4, hydrogen, carbon, oxygen, and nitrogen, the top 4 in how living systems are built, and including them as so-called functional groups. So whenever you take one of these hydrocarbon skeletons and you add one of these functional groups, then all kinds of new interesting things can happen. So adding these to the hydrocarbon skeletons, these functional groups, is going to change fundamentally how these molecules act and interact. There are 4 of these that we need to talk about here. The first one is called a hydroxyl group. And hydroxyl is actually telling you a little bit about what it does. Hydr for hydrogen, oxy for oxygen. So there it is. A hydrogen and an oxygen together make a hydroxyl group. And this one you can just stick on the end of one of these carbon skeletons, and it means you now have a hydrocarbon skeleton with a functional group. If you look at these ones here, you can do the same thing. You have a so-called carbonyl group. This is an N. And the carbonyl group means that somewhere in there is a double bond O, either at the end or in the middle. So the carbonyl group here would be something like that. And here it's just a C double bond O. But either way, the C double bond O is what makes this a carbonyl group. The third one is new because just as when we looked at the oxygen in the beginning, we now have nitrogen involved in this. And so you have carbon connected to nitrogen. They're sharing electrons here. And then this amino group is the rest of the sharing with the nitrogen. It has 2 covalent bonds with hydrogen. If you look at the periodic table, carbon and nitrogen are neighbors, and oxygen is next. So this has 4 empty spots on the outermost shell for electrons. this has 3 empty spots, and this has 2 empty spots for gaining electrons. Now this is a characteristic group for amino acids, and we'll talk about those a little bit later when we talk about proteins. And then lastly, we have a combo. This is where we have not only a single functional group, but where we really have 2. This part here, that is like a carbonyl group with the C double bond O. This part here is a hydroxyl group, but when you stick them all together, you call it a carboxyl group. So the difference between carbonyl and carboxyl is that the carboxyl has a double bond O and the hydroxyl in it. So those are the important groups that we need to know about so that we can figure out what to do with the larger molecules, and how we can actually take some of these carbon chains, these hydrocarbon skeletons, and do something useful with them. Having said this, now we can investigate how we actually make some of these larger molecules. And so let's take a look at some macromolecules. When you consider the size of atoms, like a single hydrogen atom or a single carbon atom, you realize very quickly that when you look at molecules inside of living systems, they are huge, because they can be sometimes thousands of atoms that form a single molecule. As a consequence of this, the name macromolecules is simply an indication of size. Macro means large. So these are the large molecules, and that's primarily what we find in living systems. Now, the important categories of these are carbs, carbohydrates, proteins, and nucleic acids. Now, the 3 important categories, these are true macromolecules. True macromolecules means they have repeatable units. Carbs and proteins you probably heard about because of the things that you deal with when it comes to diets. And nucleic acid is something that's perhaps not so familiar with because it doesn't play a significant part in our diet. The reason why I list those 3 is because they are constructed by taking smaller units called monomers. Monomers are the subunits of these, and when you look at that, mono means 1 and mer means unit. So monomers are the single units of these larger molecules. And then basically what we take is some of these monomers, we string them up, we can put hundreds or thousands of them together, and if we do that, then we make a polymer. Poly, most of you know, means many. So we now have many units. And macromolecules, by definition, are composed of many units. Many units. So that's how we do this. Now, let's take a look at the process by which we actually link these. Obviously, if we want to make large molecules, we have to figure out a mechanism by which we can stick those onto each other. There are 2 processes here. The first one is the one that we use to add molecules to each other, and that's called dehydration synthesis. And as before, when you look at the word dehydration, when you're dehydrated, you're missing water, right? And so dehydration synthesis means you're making something by removing water. And that's how this process works. So here is a monomer with a hydroxyl group, and we're bringing this close to a short polymer, and out of it sticks a hydrogen. These can react and form water, and when these have reacted to form water, the bond here can form. So this bond is created by dehydration synthesis. In short, lose a water molecule, create a link. And what's really neat about these kinds of molecules is that the reverse also works. The reverse is called hydrolysis. And hydrolysis means lysis, meaning splitting, by adding water. So it's the opposite process. Here we have water, we add it in, and because of the way water molecules can interact with molecules, they can literally insert themselves and have a hydrogen and a hydroxyl group attached to the different sides, and you end up with a molecule that's now split up. Both of these are very useful because when we have large molecules, obviously we need to build them, and when we digest things, we need to break things down. So hydrolysis allows us to break things down, and basically if you want to break a bond, make sure you have some water available because then you can run hydrolysis. So that's how these two very critical processes work, and that is the first part of chapter 3.